Please join me in a warm welcome for Samantha and Kaytlin.
Hello, everyone. So Sam and I both are students of Ellen Hines at the Estuary and Ocean Science Center, which is the Tiburon campus, marine campus of San Francisco State University. So we're both going to be presenting our thesis work that we've been working on for the past couple of years. So both of us have actually noticed that in our research there are changes going on both outside and within the bay and the cetaceans that inhabit both of those ecosystems. And so they are exposed to several anthropogenic threats, and we're going to kind of be talking about that today. So first, I will talk to you about entanglements and how that affects the baleen whales here. So specifically, my research focuses on 3 types of baleen whales. The first is humpback whales. And they, like most marine mammals, their populations were decimated by whaling in the early 1900s. And here in Central California, the stocks that feed here are actually still considered threatened under the Endangered Species Act. And they feed on krill, which are tiny crustacean-like plankton. And that's where most of their calories come from. However, they're generalist feeders, so they also can feed on forage fish like sardines and anchovies if oceanic conditions promote their growth rather than krill growth. And so this is this generalist feeding behavior is a characteristic that is unique to the humpback whale. So this is a range map of the stocks that summer here in California. They breed down here in Mexico and Central America, and then they feed up the entire coast of Western North America. And the second species I'm working with are blue whales, and they are a little bit more slow to recover. All of their populations across the world are considered endangered under the Endangered Species Act, and they are more specialized feeders, so they only feed on krill, or most of the time feed on krill. And so they actually, rather than switching prey and kind of staying in one spot, they will follow patches of krill wherever oceanic conditions allow that. And a study by Irving and colleagues in 2014 actually discovered 2 primary feeding spots in California. The first is at the Channel Islands, and the second is in the Gulf of the Farallones, which is just outside the Golden Gate Bridge. And blue whales winter down in Mexico and Central America as well. So the last species that I'm focusing on for my research are the gray whale. And the northeastern Pacific stock has actually been delisted from the Endangered Species Act, so that's good. They eat amphipods, which are little benthic organisms, so they live in the sediment, and they feed primarily up in the Bering Sea. But they also feed off of Central California, sometimes on their migration routes as well. So this is again just showing they feed up in the higher latitudes and they breed down in Baja California. So these animals are exposed to many anthropogenic threats, but I am going to be focusing on entanglements today. And so one of the ways that a baleen whale will get entangled is with a pot and line fishing, like this type of gear. And so this is common in crab, lobster, and shrimp fisheries. And so the whale will, be interested in the line or whatever they do. They'll get entangled around their flukes, their head, their flukes, or their pectoral fins. And they can drown if the pots are too heavy for them to get back up to the surface, or they just drag the pots around with them. And this can be very energetically costly for the animal, as well as can cause infection and makes feeding difficult depending on where they're entangled. So this is a graph actually of how entanglements have changed through time. And this is specific to Central California. So in 1993 is when these data started. And you can see that for most of the data set, we're sitting at around 7 to 10 entanglements per year in this area. But in the last few years, this number has skyrocketed. And something happened in 2014 that caused this massive peak in entanglement rates. And you can argue that increased awareness is in part responsible, but this more explains sort of like this gentle increase rather than this giant spike. So the point of my research was to predict what influences entanglement rates, whether that be local oceanographic conditions or full Pacific-wide basin scale environmental variables. Yeah. So first, I'm going to kind of describe these variables that I'm using. I created several sets of models in order to answer my question. And the first is the Southern Oscillation Index. That's the one most of you have probably heard of. It represents the El Nino and La Nina cycles. And so the positive, are denoted in red here, is actually the more productive phase. And so during La Nina phases, we get colder water and a deeper upwelling cell, and so we get more nutrients in that instance. And then the next is a Pacific decadal oscillation, and this rotates every decade or so, sometimes longer. And during the negative phase, which is in blue, that's when we see cooler, more nutrient-rich water. So that means more productivity and theoretically more whales in the area. And the last is the North Pacific gyre oscillation. And here we care about the positive phase, which is when we see stronger currents and a deeper upwelling cell, and so we see more nutrients coming to the surface and higher productivity. I'm also using local variables because this is where management strategies will be taking place. And for those, they're centered at the Farallon Islands, which are about 48 kilometers from San Francisco, so it's like 20 miles or so. And it's located within the Greater Farallones National Marine Sanctuary. And so when I talk about local variables, I'm talking about with them in respect to this point. So I looked at temperature, salinity, temperature fronts, the upwelling index, and the spring transition date. And the spring transition date is when the upwelling season starts. So now we're going to talk about my questions. And the first question that I asked was, how have whale timing of arrival and peak and departure changed, and what are the drivers of those changes? So which variables that I just talked about influence what time humpback whales, for example, arrive into the system? And then also, this question is set up similarly to the first one, but this one deals with how entanglement rates have changed through time and which of these drivers influence the differences in entanglement rates that we're seeing. And then, can a predictive model be used to manage this system? Can we predict when these entanglements are going to happen so we can prevent them? So now we're getting into my methods. And I have a lovely data set, it's beautiful, of 30 years of daily whale counts from Southeast Farallon Island, collected by Point Blue Conservation Science, so huge shout out to them. The counts were taken at the top of the lighthouse, which is about 90 meters above sea level, and using binoculars, and they identified counts to the species level. And this figure here shows how far out you can see, and these ones are about 30 kilometers out, but you can see that most of the counts were actually taken within about 15 kilometers of the island. So when I collected, and this is basically what the data looks like. So this shows humpback whale counts, and each line represents 1 year of data. And the observations are on the y-axis there. And so the individual years aren't important here, it's kind of a messy graph, but what I want you to see is that the peak, the magnitude of each peak and the width of each curve are different for each year. So this means whales arrive at different times and they stay for different amounts of time, and that's very common in the variability of these whales. And blue whales actually show a similar pattern to the humpback whale. That's in contrast with gray whales, which have 2 distinct peaks. And so they come here, they show up in California when they're on the migration typically. So we see a peak when they're going south and then when they're coming back north. So this calendar is a little bit different than the last one. It starts on July 1st, and that's because January 1st is in here somewhere and it would have cut off this peak. So to analyze these data, we used an offset year starting on July 1st, as well as we cut this in half, or we cut the data here on February 15th, so that we could analyze the southbound and northbound migrations separately. If that makes sense. This is how my models were set up. Realistically, it's a lot of code in Stata, but this is a pretty way of displaying it. So I performed linear regressions on whale timings of arrival, peak, departure, and residency time as the dependent variable, and the independent variables were both annual and seasonal environmental variables that I described earlier. So how did I calculate the timing of arrival and things like that? If we picture this curve as one of those curves in the graphs that I showed you earlier of annual whale counts, the 10%, or the day when 10% of the annual populations were counted is when I denoted that as the arrival day. So when 50% of the whales were seen for the year, that was the peak, and 90% was the departure. And residency was calculated by subtracting the arrival by the departure day. So I'm going to be showing several slides that look like this, so we'll walk through this one really slowly. The graphs all have year on the x-axis, so which displays the arrival day by time, or through time. And then on the y-axis, we have the day of the year, or the average day of the year. So 0 is the average, and then it's the difference from the average. And this table shows the significant variables that contributed to this model, but the important ones are in red, and those are the most commonly significant variables throughout all the models. So those are the ones that might be important for management purposes when you're looking at several species at one time. This graph shows that humpback arrival has become earlier through time. And this is by about 100 days, which is really significant. That's a full season earlier than they used to arrive, which is quite drastic.
Is there a threshold? Like if you saw one oddball one way ahead, would you still call that?
So that's what I tried to do with the 10%. Okay. So that got rid of theoretically most of those oddballs. And again, that's why a lot of the gray whale data set had to be kind of shaped a little bit so that we got rid of the oddballs, and the gray whales have like a resident population here, so that helped get rid of that too. But so this displays the peak, and so this has also become earlier through time, and we see that sea surface temperature and the Southern Oscillation Index are important variables in this one as well. Humpback departure has stayed approximately the same though we do see some variability, but only by about 10 to 20 days. So the main thing from the humpback timing results is that they're arriving a lot earlier than they used to. Now we're moving on to blue whales, and the only significant year term here was for the arrival day. So the peak and departure for blue whales haven't changed through time, but they have been arriving a lot earlier, very similar to the humpback whales. Again, by about 100 days. Gray whales on their northbound migration, the peak has just kind of sort of varied through time. We see that they peaked a little bit later in the season, in the mid-2000s, but really these just so kind of varying through time. And the departure shows a very similar pattern. Yeah. So the answer to my first question, sorry, it's blocked out. Whale timings have changed through time. And the most important drivers of those changes are the Southern Oscillation Index, sea surface temperature, and North Pacific Gyre Oscillation. So now I'm going to talk about how entanglements have changed through time. I set up a very similar model. I used a linear regression, and I used whale timing and sightings variables. Yeah?
What is linear regression?
Yeah, so basically what that does is it just compares two variables. So if you look at like a scatter plot, it calculates the average line that you would make through a scatter plot.
Thank you.
Yeah, no problem.
Do we know why there was a peak in the 2005 across most of the species?
I haven't figured that out. There's something that something happened. It might have been a oceanographic thing that we just don't know about. It might have been something to do with the counting that happened. Maybe those years more people went out or something, or just the days were better so that you could see farther. But yeah, I haven't really figured it out yet. Yeah, we can go. Okay, so we kind of already saw this in the graph that I showed you at the beginning, but specifically humpback entanglement rates have drastically increased through time. And more specifically since 2010, 2012, that's when we see that huge spike. Gray whale entanglements have also increased through time, though not as much as the humpback whale. Their entanglement rates have increased by about 5 times, whereas gray whales, if you look at the y-axis here, have only increased by about 0.7 times. So this again might just be because of increased awareness, something like that, but something else is going on with the humpback whales that we really need to focus in on. So we're bringing you back to this graph to show you now the differences in species. And so this is the relationship that I modeled is demonstrated in the actual observed data as well. So gray whales have just kind of varied a little bit through time here, but humpbacks, again, we see this huge spike in 2015, 2016, and we actually see our very first recorded blue whale entanglements in Central California as well. So gray whale entanglements have stayed close to the same, increased a little bit, but blue and humpback whales entanglements have increased a lot through time. Yeah, and these are the important drivers, PDO and sea surface temperature. So now we're going to look at to see if a predictive model can be made and help predict when these entanglements will increase and hopefully help reduce the number that we see. And so I created a forecast model, and the important thing here to note is that I used the whale timing variables and the previous season of the environmental variables that I used. So let's say humpback arrival happened on June 1st. I only inputted significant variables from the previous models that happened before that date. So,
what effect does population size have?
I actually did that as well, but I cut that out for this part because the timing is a little bit more interesting. But humpbacks and blue whales have increased through time. Gray whales haven't really, there's been some like varying levels of how many we see. It's also difficult because of the study area that I have. It's very confined. So, you know, if they move 15 kilometers outside of the island, then I won't see them, but they're there. So it's hard to delineate exact like population trends from my data. Yeah. So the model that I created, the predictive model, lost about 50% of the accuracy when compared to the full models that I created, the full timing models. So they can work, but they're not that great yet. And that's okay, because this was just a first look at that, this sort of analysis. But once we get better at predicting things like sea surface temperature into the future and how whales react to certain things, then I think that these models could be a really, really good tool in predicting entanglement rates and reducing the number of entanglements that we see. That's basically what I've already said, so we can move on to the cool stuff. Okay, so I'm gonna throw a disclaimer out there. This is just what I'm seeing. I'm not a manager or anything like that, so I don't know if you guys are part of this fishery or not, but yeah, this is just a kind of what I'm seeing in the data. So the California Dungeness crab fishery is responsible for the most entanglements that we see in both gray and humpback whales. Their season is open from about mid-November to the end of June. And yeah, we can move on to the next slide. And so theoretically, when the season is closed, there are no pots in the water. But there are some things like ghost nets that we have to worry about and left gear, but let's just say that when the season's closed, so during this blue box, there are no pots in the water, so there's no risk of entanglement. Each black bar here represents the residency of the humpback whale. So the top is when they arrived, and the bottom is when they departed this system. So if you click the next one. So these years here, we see that they arrived much earlier than this close date. So they had an increased interaction with the gear. This might be one of the reasons why that we see the increased entanglement rates, especially in humpback whales, because gray whales don't show this pattern because their residency time is in the winter, so they're always exposed to the full extent of the fishery. The only other 2 years where we saw early arrival was in 1997 and 2005, and those were both really anomalous warm years as well. If you remember, I don't know if you've heard about the really serious El Nino in 1997, and there was also a really big warming trend in 2005 as well. So I'm sort of looking at these data and looking at these patterns to hopefully create a tool to prevent the entanglements, but just because I'm doing a master's thesis, so it's not quite there yet, but hopefully somebody else will be able to take it on and refine it, make it perfect. But until that happens, there's lots of stuff going on to help reduce the entanglements that we see in Central California. There is an entanglement or disentanglement group, a working group that is altering gear and figuring out best practices so to reduce the amount of interactions that we see. EcoCast from the Lewison Lab at San Diego State is looking at fisheries and bycatch and overlaying them. And so you see which areas are best for the fish, but with the least amount of bycatch. And then Happy Whale is a citizen science group, or a citizen science-based project that you input pictures of flukes or any other sort of individual identification. And then this is tracking how far and wide whales go. And then Whale Alert is an app that was created to alert both managers and the commercial shipping when there's whales near the shipping lane so they can slow down or move or whatever it is. So there are things that are being done to mitigate this. right now, and hopefully my models will help with that. So I'm done talking now. Sam, if you want to come give your talk, if you guys have any questions on mine, or if you want to wait to the end, whatever you guys feel like doing.
I have one
Yeah.
question. Do you know anything about the whale that washed up at Tennessee Valley, the gray whale?
Wait, was that the one that was hit by the boat?
I don't know that. That's what I wanted to know. It's a 35-foot female that washed up last Friday.
It was, according to Bill Keener, it was massively entangled.
Oh, it was entangled.
And it was, I think he said it was an adult female.
Yeah.
I have pictures. I was there this morning.
Oh,
I saw it. It's amazing.
Yeah.
It's worth the walk.
So was it like, so you could see where it was?
No, I couldn't. That's
Oh.
why, because I think the Marine Mammal Center or Cal Academy have been in and taken big sections
Yeah.
out of it that probably has something, but the eye is still open.
Ooh,
So I have a wonderful
weird.
picture. It's weird, and I'll show it to you after.
Yeah, I'd love to see it. Yeah. I helped Cal Academy do a necropsy of a blue whale that washed up in, where was that? Bodega
Uh-huh.
last
Is
year.
that Mo Flannery? Did you
Yeah.
work with Mo?
Yeah.
Okay.
So that was a cool experience for me, but very sad, but also my nerdy side was like, yes, that's so cool. Yeah.
I think there's been some variation in the crab season a little bit,
Yes.
either due to domoic acid or, price or whatever kind of thing. Have you looked at that, like in any given year where they might have had a shorter or longer season, did that seem to influence them?
So actually right after I gave my defense, one of my committee members was like, how come you didn't look at that? And I was like, I didn't even think about that. I didn't know that it changed, so that is something I'm going to incorporate if I have the time. Hopefully I will. But yeah, I mean, that's obviously a huge contributing factor also. So how big that blue bar is, right? Yeah, so hopefully that gets
What would be required for these whales to go from endangered to threatened to delisted? Is that a population number in a certain area?
Yeah. I don't know what the population number is off the top of my head, but yeah, so that they're sustainable populations, basically. Yeah, no problem. Okay, cool. Sam, you want to go?
I can hold it. I can hold it.
Oh, great. Stop pushing that button.
Okay, so I'm Sam, and I'm going to speak to you tonight about my research, which is looking at another threat to cetaceans, which is underwater noise. So as many of us who live in the Bay Area know, the San Francisco Bay is heavily impacted by human activity. It's home to the Port of Oakland, which in 2016 was ranked 6th in total volume of containers in the country, and 60th in the world. So there's a lot of traffic coming in and out of that port. The city of Richmond is the site of a Chevron oil refinery, where large cargo and tanker ships regularly come and go every day as well. And pretty much any day, if you look out onto the water, you can see that recreational traffic is abundant as well. But just outside of the bay are 3 of our national marine sanctuaries, where wildlife is abundant. These sanctuaries support 37 species of marine mammals, 10 of which are threatened or endangered. And so the habitat of these animals, especially when they come into the bay, overlaps with all of this busy vessel traffic. So, I'm sure you're aware, we have some humpbacks in the bay. In 2016, they came into the bay to feed in unprecedented numbers that we hadn't really seen before. And last summer, they did the same thing, but even with greater numbers, and unfortunately faced interactions like the one you see here. And recreational boaters just might not be used to whales, such large creatures, being in their space, or might not even be aware that they're present. So besides humpbacks in the bay, there are a number of other cetaceans that come in as well. And GreatWill likes to stop in on their migration route, like Kaytlin talked about in her talk. We've actually seen a number so far this year, and even farther north than we are right now in the bay. They've been up there in the North Bay quite a few times. Next is the harbor porpoise. And we know from fossil records that the harbor porpoise was historically in the bay. But in the past roughly 100 years, they haven't been here. But thanks to researchers, local researchers, we now know that they're back in the bay foraging every day of the year. Bottlenose dolphin also occasionally come into the bay. The Southern California stock has been expanding their range northward, and we actually have 2 residents in the East Bay that stay there all the time. So this is a sight too common in recent weeks in the bay. And when cetacean habitat overlaps with heavy human use, there can be a number of consequences. The first is vessel strikes. And this female GreatWill, unfortunately, was determined to have been killed by a vessel strike before she washed up near Oakland recently. So Kaytlin talked to us about entanglements. But today, like I mentioned, I'm going to focus on underwater sound and how this may threaten the cetaceans that we have in the bay. So first, let's talk about some sound concepts. It took me a long time to get used to them, so I'm going to break it down for you too. So light. When I first started, I found it easiest to understand concepts about sound by relating it to light. I don't know if it was just my own education, but I felt like I learned a lot more about the light spectrum than I did about sound growing up. So it was kind of easy for me to compare the two. So both sound and light travel in waves. And light travels in electromagnetic waves. So if you go outside and look up at the sun, or if you go out at night and look up at the moon or the stars, you can tell that light can travel through a vacuum, right? Because space is a vacuum and we can still see the light. Now sound travels in waves, but it requires a medium because the particles basically get energized and then bump into the ones next to them, which energizes the ones next to them. So it needs a medium to get transmitted. So this makes water an awesome place for sound to transmit. In fact, sound travels a lot faster in water and also can travel farther. If anybody has heard of the Heard Island feasibility test, this was a controversial experiment where scientists wanted to see how far a sound could transmit underwater. So they went to Heard Island, which is in the southern Indian Ocean, and made a really loud sound underwater. And sure enough, at all of their receiving stations across the world, they were able to hear that sound. So this showed us that sound, if it's loud enough and if it's low frequency, can be heard across entire ocean basins, which is pretty amazing. So this is another figure that I saw a lot growing up. You're probably familiar with it. It's the electromagnetic spectrum. On the left side, we have really long radio waves. And so we can't see these, but they're there. They have really long wavelengths. And as you work your way to the right, the wavelengths get shorter, and then we start to come into the range that we can see, which is the visible light. Then the wavelengths get a lot shorter to the right, where we have X-rays and gamma rays, which I'm sure we've heard of, but we also can't see. Now, sound is similar. So here we can see on the left side are the lowest frequency sounds, and these are below what we can actually hear. And then as we make our way to the right, we get up into the sonic sounds, which we can perceive, and then into the ultrasonic and hypersonic, which is actually above what we can hear. All right, so the piano is a great representation to see pitch and frequency that most of you are probably at least a little bit familiar with. So the low keys on a piano are low in frequency, they're low pitched. And as you work your way up to the right, they get higher in frequency, higher in pitch. And the red lines show octaves. Okay? So an octave is 2 notes that are the same pitch, so they sound very similar, but the higher one is twice as great in frequency. So you can see the frequencies down here of a few of the octaves. And hertz just means vibrations per second. So as the notes get higher, we get more vibrations per second. So for those of you that are not super musically inclined, think about what Dorothy might be singing here. Okay, so if you think about the first two notes of the sound, or Somewhere Over the Rainbow, I would sing it for you. I wish I could, but I won't. So those two notes are an octave apart. So that kind of gives you a reference. There's a lot of frequencies in between, just in an octave. One more. Oh, you got it. Okay. So this shows the range of human speech. And then, as we just saw, I'm going to see again, baleen whales are more sensitive to sounds in the lower range, okay? And sometimes even below what we can hear. And oppositely, dolphins and porpoises are more sensitive in the higher range, and sometimes even make sounds that are beyond our hearing in the upper range. Okay, so one last light and sound comparison. So light of the same color can have another property, and that's brightness that we see right here. So for sounds with the same frequency can have different loudnesses, right? So it can be the same pitch, but be a different volume. So if you're pressing a piano key really softly, it's going to be a very soft sound, but if you press that same key, that's the same pitch, really heavily, the sound's going to be a lot louder. So, two key concepts to remember about sound: frequency, which is kind of like the pitch, whether the notes are low or high, and loudness or sound pressure. So what does this all mean for cetaceans? Cetaceans evolved under conditions where underwater sound was mostly driven by natural sounds, like wind and wave action. So if you think about the sound of waves on the beach, it's nice, or the sound of wind outside your house, these are relatively high-pitched sounds. So these are what the whales were used to as they evolved. But across the last few hundred years, throw in tanker ships and cargo ships, and these are much lower in frequency sounds. So it's thought that these whales who are really long-lived won't be able to genetically adapt to this new sound that's in their system as fast as we're putting new vessels and new sounds into their environment. So their responses to this sound have been classified in the following. So the first is just, can they hear the vessel if it's near them? And then second is a behavioral response. So some cetaceans have been observed foraging, and then a boat will come into their area, and then they'll give up and they'll leave. And this has been observed in a multitude of species. Next is masking. And this is a great way to understand this is the library analogy. So if you're in a library and you're at a book club and you're in a circle and you're whispering to each other because it's a library, it's trying to be very quiet. If some people come in the library and they're talking really, really loud, they're being really raucous, you probably won't be able to hear yourselves whisper to each other anymore because the sound in the area is louder than you are. So you might have a few options. You could maybe increase the sound, try to talk over them. You could leave the area, or you could kind of just give up what you're doing in general. And this is kind of what we see in cetaceans when they can't hear each other or sense their surroundings over the din of the other sound. So these are kind of the significant factors we see influencing them from vessels. Beyond that, we have some physical injuries. A temporary threshold shift is where you temporarily lose a frequency. If you've ever been to a really loud concert, you might have experienced that. The next morning, maybe you have your senses are dulled a little bit, but then by the end of the next day, you've gotten back to normal. This occurs in cetaceans as well. And then finally, permanent injury can happen when the same sort of thing happens, but the sound is so loud that it physically damages their ear systems so that the next morning they don't have that frequency back. Then they've permanently lost hearing, at least at that frequency. Okay. So a study in 2014 looked at different sound levels across the western coast of Canada. And so they looked at two locations, and one was a very busy port area near Seattle and Vancouver. This might be similar to what conditions could possibly be here in the Bay. And then they compared that to a location, a more rural location with a less busy port north of that. Okay, so here's the spectrogram from the northern, less busy location, and I'll kind of orient you to what you're seeing in the spectrogram. On the x-axis is time, so it's just time going by as you go left to right. And then on the y-axis is frequency, so if you remember, so the pitch is going up as you go up the graph. And then the color and the brightness of the color is how loud the sound is, or what the pressure is. Okay, so you can see the influence of wind up in the higher frequencies, but then you can see an occasional vessel come by and they're pretty loud. So let's compare that to the other location. And you can barely see any sort of background noise like wind. It's completely dominated by vessels. So the authors actually found that the communication space that the whales had in this area was significantly decreased compared to the area that was less busy. With cetacean species coming into the bay more frequently, I wanted to see what kind of acoustic conditions the vessels put them under. So I have some research questions. The first is, do vessels influence underwater noise in this area at all? How loud are the vessels? And then where is the sound loudest in the area? So in order to do this, we need to know about the vessels. We need to know where they are and what they are. And one method of doing this, you may have heard about, is using the Automatic Identification System, also called AIS. And this is a legal requirement that large vessels have to transmit both vessel and voyage data to each other, and then also to land-based stations. And then the public can actually get access to that data. But smaller vessels are not required to transmit AIS data. And this has left them out of a lot of studies on cetaceans and sound. Because the AIS data is so easy to come by, this data is a lot harder to get. So using marine radar technology, we can actually see where those smaller vessels are. Because most boaters use marine radar to kind of see where they are on the water, see hard objects ahead of them to avoid collisions and things like that. So we can put a radar sensor on land near the water and use it for the same purpose, to track vessels that are nearby. So shown here is the Marine Monitor, or the M2, and it was developed by a company called Protected Seas. And it does this, it integrates the AIS and the radar data. And it's located at the EOS Center where we go to school. It's in the northern Central Bay. And it was originally designed to autonomously autonomously monitor remote MPAs. So it can track vessels kind of on its own and then send off the data to somebody who's interested in it. So this version here in Tiburon is kind of an advanced demo. You can see that we have solar panels, so it doesn't need to be powered. So it's pretty cool. And it's novel in its design as it integrates both of these things. So we have the AIS sensor, which is here down at the bottom, and then we have the marine radar, which I'm sure you can recognize up there at the top of the tower. Now, AIS data gives us the vessel's identity, but marine radar is just like a blip on the screen. We don't really know what it is, we just know it's there. So this system actually has a camera, and you can kind of see it below the radar, that logs photos of every unique vessel that the radar sees. So then I get to look, go a few more.
Oh,
That's fine.
oh. That's where we
So then you get to see, you can actually identify the vessel from the photos. So this is kind of what we get to work with from the system. On the right, you can see the map of where the vessel went. And then on the left, you can see the photos. So in this way, I can manually go through the photos and see, was this a recreational craft? Were they fishing? Was it a sailboat? Things like that. So it's pretty cool. We're kind of creating our own data set there. All right, so the data comes in as little point detections, as kind of like location reports. So it tells us how fast the vessel is going and where the vessel is. And we get these about every 2 to 6 seconds from each vessel. So it is a lot of data, but it's pretty cool. So the study area is defined, I chose to define by the maximum range of this marine radar system. So marine radar can't really see past hard objects because That's what it uses to detect an object. And in the bay, there are a lot of hard objects, a lot of hard boundaries. But even though our study area is a little bit restricted, it still captures all of the traffic that comes to and from the Port of Richmond, as well as things that go upward into the Delta, and then also recreational traffic in between the multitude of marinas that we have in the bay. So the hydrophone was in the water at the EOS Center, just next to the M2 sensor. You can go ahead and click through them if you want. So it's here on our pier, submerged about 30 feet in the water. And we recorded 12 days of continuous data in February. And I was interested in looking at the full spectrum of sound, which is called broadband. So that's pretty much what everything that the hydrophone can capture. But then I was also interested in looking at lower frequencies and how they compared to sounds in the higher frequencies. Because if you remember, baleen whales like gray whales and humpbacks, they are most sensitive in those low frequencies, while small cetaceans like the harbor porpoise and bottlenose dolphins are more sensitive in the higher range. So I wanted to be able to compare those two. So, do vessels influence noise in the study area? Okay, so basically, like I said, we recorded data continuously for 12 days, and I broke up all of those audio samples into 10-second little chunks, and I binned them by hour, okay? And then I took the average sound at the hydrophone per hour, and that's what this graph here represents. So you have hour on the x-axis, and you can see that sound was lowest at night, like we might expect, and it steadily grows throughout the day, peaking around 3 p.m. And then the average vessel count, okay, so I counted the average vessels per hour also, and if you look, just looking at the graphs, they're very, very similar, okay? But I was also interested in how wind and wave action might influence the sound as well, because we know those are important. So I took data from a local NOAA buoy and averaged the wind speed per day, and saw that the wind speed really wasn't maybe as related as the vessels might be. So I plan on statistically comparing these to see how related they actually are, if it's significant. But qualitatively, you can kind of start to see that the sound of the hydrophone is probably most related to the vessels in the area. So how loud were the vessels? So we know that there were loud conditions at the hydrophone, but the vessels can be any number of distances away, right? So the sound at the hydrophone might not be the best representation of how loud an individual vessel was. So I had to bring in a model, and I had to determine how loud each vessel was at its source. So we know that sound moves well in a medium, but the density of water and other properties eventually cause the energy to run out, similar as it does in air. If we only speak so loud, it's not going to be heard really far away. The sound energy is going to die out before it gets to you. So this is what we call transmission loss. And it's a function of these factors. So spreading loss, which is just basically how far away you are from the source and then the receiver. And then the absorption loss is controlled by a lot of other water quality factors. So I used the data from the M2 sensor to determine how far away the vessels were from the hydrophone at their closest point of approach. And then I paired that with the acoustic data, and then we had bathymetry data from NOAA, and we actually have a monitoring station at the EOS Center that monitors these water quality parameters, so we could match all of those things in time with the vessel. So ultimately, once I calculated the transmission loss, all I had to do was add it to what we heard at the hydrophone, and we could tell how loud the vessel was out there at its source. So these were the results of all the vessels that we saw across those 12 days. So we saw bulk carriers, vehicle carriers, crude oil tankers, chemical tankers, a lot of commercial ferries, and a lot of motorized recreational craft. So just to kind of orient you here, the darkest blue is broadband, so the entire range of what we could see in the hydrophone. Then the next lightest blue is that low frequency sound, and the lightest blue is the highest frequency sound. So really just looking at this, you can see that the highest frequency sound was not as loud as the low frequency sound. Now, where is the sound actually loudest? So basically, I used these exact same concepts to be able to back calculate the received level now that we knew the source level. So now that we know how loud a vessel is, as it comes into the study area, we can actually model how loud it is as it goes through, because we know how loud it is at its source, and we know the transmission loss. So I needed a way, basically, so the received level, that's just if you're listening to the hydrophone, kind of like a microphone, we hear a certain level at a point in time, but that can fluctuate, right? And it probably fluctuates as the vessel gets closer and then goes away from the hydrophone. So we needed a way to accumulate sound through time. And the sound exposure level is recommended by a lot of cetacean scientists because it accounts for time and how loud the vessel was. So basically it normalizes everything to 1 second so that sounds can be compared that are really long and that are also really short. My analogy for this one is a giant piece of birthday cake. So this is kind of what helped me understand this really kind of difficult concept. So if you go to a birthday party and somebody gives you a big piece of birthday cake, it's got all the icing and ice cream, and you scarf it down in 1 minute, you got a lot of calories really fast. Now, say you do like the polite thing and take like 10 or 15 minutes to slowly nibble your birthday cake, you're still gonna get the same amount of calories, right? Even though you ate a little bit slower, you're still gonna probably get the same physical result. Now this analogy kind of breaks down, like if you took 24 hours to maybe eat that cake, then like your digestive system would start doing some other stuff, but you get the idea. So I used the received level that I was able to calculate and then was able to incorporate time. Okay, so what I did was I calculated the sound exposure level for each unique vessel trip through the study area. And then I just summed all of those through time. So the numbers here are not actually that useful. It's more useful to look at the trends. And this is for large ships. Go ahead and do one more. So you can see that the sound was actually loudest where we kind of had that merging of the two paths that the ships tend to take. So you can see that most of the ships went to either the port of Richmond, or maybe they were going up northward or coming southward out or in from the delta. And our loudest point was where those two kind of passages converged. So ferries are all over. I'm sure you guys are all local. You know that the ferries run almost all day, every day, over a large portion of the water. So their sound is more pervasive across the entire study area. And you can see that based on their tracks. So finally, the motorized recreational craft, their sound was more dispersed because their tracks are very dispersed as well. So in the future, I'm still trying to figure out the best way to calculate and to represent sound over space and time. Because if you imagine a cetacean, they're really mobile species. So the chance that they stayed in one of these little cells for even a second, or let alone the entire 12 days of my data collection is really unlikely. So in the future, I'll be looking for a way to kind of quantify that in a more meaningful way for cetaceans. But hopefully this can kind of give you an intro and kind of see how that sound is dispersed across the study area. So in conclusion, vessel sound dominated the underwater soundscape of the study area. And the sound was loudest in lower frequencies, but also present in the higher frequencies. If you remember that box plot with the really light color blue, the sound, it was not zero, right? So we're still having some high frequency sound, it's just not as loud as it is in the lower frequencies. And then the sound from vessels permeates across the entire study area. So these results can really start to help marine mammal researchers understand the conditions that these cetaceans are under when they come inside the bay and decide maybe if there's any management actions that need to be taken. So we would like to thank our supporters, both moral and financial. This is our lab, this is all of our coworkers at school, and our awesome advisor, Ellen Hines, that you may know. And I want to say a special thank you to this chapter of ACS. Like Kaytlin mentioned, we got to go to the Marine Mammal Conference in Halifax, Nova Scotia in October, which was amazing. Being a grad student, we're so like in our own world, really caring a lot about just what we're studying, and getting to come and speak to people who really care about it and care about these animals is awesome. So thank you. So I think that Kaytlin and I's research, there's one more slide. Kaytlin and I's research kind of highlights what it's like to be a cetacean in the Bay Area and what they might be up against. So we really think that it's important that, as we share the Bay Area with this like growing and changing population, it's important that we look at the practices that we're just kind of used to and really ask if they're sustainable. So, thank you. Did you have a question?
Sure. What role, if any, does wind speed affect the underwater sound trapping?
Yeah, wind speed does influence the underwater sound, but I think that what I've seen and what I've looked at is that that's kind of masked and overtaken when there are loud vessels in the area. So most vessel sound is broadband. So it's covering the entire frequency range. If you remember those really colorful spectrograms, when a vessel came in, there was red just all the way up at all frequencies. And that's because the sound from their propeller is really low pitched, but then all of the bubbles and all of the things that happen when the propeller spins kind of creates sound at those higher frequencies. And so even though wind and great winds and wave action and things like that are important on the underwater sound, they're a lot of times they're masked in areas that have a lot of other anthropogenic influences. Yeah.
It seems like in the last 4 years or so, there have been more sightings of whales inside Point Bonita. I don't know if you have any data on that, whether that's accurate or not, or if it's just sightings or...
Yeah, I don't have any hard data on that. I like to kind of follow when the whales are in the bay and when they aren't. And so I do know just kind of on my own observation that they have been increasing. And I know that they were seen actually inside the gate feeding, like I mentioned all the way up back at the beginning, for the first time in a really long time, actually inside the gate in 2016. So as Kaytlin mentioned, I think that there are drivers that are kind of changing maybe how far they have to come in. When they're coming in, they're foraging and they're feeding on those forage fish. So if you remember Kaytlin's presentation, she talked about humpbacks being generalists. So if there's krill in the area, they'll feed on krill. If there are anchovies in the area, they'll feed on anchovies. So it's kind of been hypothesized that maybe the years that they come farther in are years that maybe krill isn't as abundant and they have to come in looking for forage fish. Like I said, there's no hard data, but that's kind of a theory of what's driving that change. Yeah.
So the spectrogram showed all the sounds that were happening at once, but the following slide had groupings of broadband and high and low. And can you repeat which one was the most common in the bay? High, low, or broadband?
Definitely low. Well, broadband is going to be the greatest no matter what because it incorporates the whole thing. But the low frequency dominates for sure.
Okay.
Yeah.
I heard that the first time. I just wanted to double check.
Yeah. Which is expected. And it's funny, it's kind of like a back and forth. People kind of assume that the low frequencies are going to be more pervasive. But a lot of times, because of hydrophone technology, it's harder to record the higher frequencies. So a lot of times people are like, oh, well, it's more pervasive, but we also didn't measure in the high frequencies. So I tried to kind of actually take advantage of the hydrophone that I had and be able to compare the high to low so we could actually see what the real situation might be.
Yeah, a picture might emerge because there's sightings of harbor porpoises really high up, and they are in the higher frequency above dolphins.
Yeah.
And wouldn't be disturbed by those low frequencies as much.
Totally. Anybody else?
What's next?
What's next? Well, so Kaytlin has successfully defended her thesis. So my work is still a little bit of a research in progress. Like I mentioned near the end, I really want to really hone in on some specifics that we could maybe potentially communicate to managers and really get a quantitative idea of what it's like for them out in the bay. Yeah, thank you so much.